Okay, horizontal asymptotes and how to cross them. To find the horizontal asymptote, we will compare the degree of the numerator with the degree of the denominator, which will produce three cases. Okay, so let me kind of say what we're saying here. So if you look at your highest exponent, or the degree of the polynomial, we're going to look at the exponent of the numerator and exponent of the denominator. And so to shorthand this, we're going to refer to this degree m and degree n. Okay, if the numerator has a larger degree than the denominator, or bigger, sorry, if it's bigger, then there is no horizontal asymptote, there is no HA, but there is an oblique, or slant asymptote. And we'll get to that case a little bit later on, but there's in that, if it's what's affectionately called a top-heavy rational, then there's no horizontal asymptote, it's something else, and we have to handle that a little bit differently than these other cases. If the numerator and denominator have the same degree, then we're going to look at the leading coefficient, and the equation for the horizontal asymptote is a over b, meaning the leading coefficient of the numerator over the leading coefficient of the denominator. And that's the same case, and if m is less than n, so if the numerator's got a smaller degree, then it's the horizontal asymptote is y equals 0, and that's what we call a bottom-heavy rational. Okay, so one of three things, depending upon the top-heavy, bottom-heavy, or same of your rational. So let's take a look at some examples of this. And again, the goal here is just identify the horizontal asymptote. Okay, so in this first case, so look at that. Numerators match, they have the same exponent, so it's what we call the same case. So I want to look at the leading coefficients. And so even though we don't see a number, you can imagine there's little ones written right there, right? And so our HA in this case would be y equals 1 over 1, or just y equals 1. Okay, in the next case, so we're going to look at leading coefficients, and I notice that it is bottom heavy. It's got a larger denominator, the larger degree is in the denominator, so it's a bottom heavy rational, in which case the HA is y equals 0. Okay, and in the third case, again looking at the leading coefficients, this is what's considered to be a top-heavy rational. And since right now we're just asking about the horizontal asymptote, there is no horizontal asymptote in this. There is something else though, and we'll get to that case in a moment. Now, with vertical asymptotes, we have this rule that says you cannot cross them. But with horizontal asymptotes, you don't necessarily have that case. Okay? So in a rational function, there will be at most one horizontal asymptote, and the graph may cross or touch the HA. Okay? So it is okay to cross the horizontal asymptote, but not in the long run. So just real quick, what does an HA measure? Let me kind of show you real quick in this graph right here. So here we have, you can kind of see that there's an asymptote right there. In the long run, it's going to get really, really close to 0, but it's not going to go above 0. And same thing here on this side. I'm going to do some points here. So on this side right here, it's going to get close to 0, but it's not going to go above 0. And on this side, it's going to be above the x-axis and get really close to 0, but it's not going to go below it when you look at larger and larger x values. But in the middle of the graph, right there, it actually crossed the horizontal asymptote. So the horizontal asymptote is a measure of what happens to the y values in the long run. That means in the short run, in the middle of the graph, it's okay to cross. Okay. In this second example, okay, here's our HA, and you can see that it actually does cross right there. Crosses it in the middle of the graph. But again, in the long run, so when we look at that part and that part, and this, this side right here on the left, it's going to stay above the horizontal asymptote and never go below it. And on the right, it's going to stay below and never go above. All right, but no, it's kind of, you can see how they're hugging it though. So in either case, it is okay for the horizontal asymptote to cross it in the middle of the graph, but not in the extreme values. Now, with that idea in mind, we can actually figure out where it crosses at. So what we're going to do is we're going to set the function equal to the horizontal asymptote. And then we're going to solve for x. And this is going to give us the x coordinate of that point. And then to solve for y, the y value, we're going to substitute into the reduced function and solve for y. And then find any points, if any, where the graph crosses the HA for the last three. Okay, so we're going to go back and look at those previous examples. Okay, so let's kind of go back. Come on, scroll up. All right, let's go back here. And let's look at our HAs again. Let me kind of get some more room here. So here we said our HA is y equals 1. And let's look at the question, does it actually cross the HA at any point in time? So I'm going to set the equation x squared minus 1 and x squared plus x equal to 1 and see if I can solve for x in that case. And let's see. So I want to bring over okay, so if you remember this x squared minus 1 over x squared plus x, we'd actually already factored that out and identified a hole in it because we did x we did x minus 1, x plus 1 over x times x plus 1, and the x plus 1's divide out. So we're left with x minus 1 over x equals 1. And then I'm going to multiply across to get x minus 1 equals x. Now, when I subtract x off of both sides, I get negative 1 equals 0. Well, that's clearly not going to happen, right? So I tried to solve for where it crosses the HA. I didn't get a solution. So this one does not cross. The horizontal asymptote. Okay, in this case where it does that. Let me go to the next one. So here we set our HA as y equals 0. So again, let me get myself a little bit of space here. So I got 0 equals 5x minus 2 over 3x squared minus x minus 2. And since I'm dealing with, well, yeah, let's do that. Let's see if we can factor this, or we actually did factor this earlier. So we get 3x plus 2 and x minus 1, all of which equals 0. So if you kind of think about this, we're going to cross multiply. So I get 0 times the 3x plus 2 times the x minus, that still gives me 0. So I get 0 times 5x minus 2, which does allow me to solve. So add 2 and add 2, so I get 2 equals 5x. So divide by 5. So here I get x is 2/5. So I know it does cross it at the ordered pair of 2/5 comma something. And so all I have to do at that point is evaluate 2/5 in the original function. So what is f of 2/5. So 5 times 2/5 minus 2 all over. Now I'm going to write this, but hold on a second, because you might not have to write this out when you see what's about to happen. Okay, so I want to simplify that out, but the thing is, up top, I'm multiplying by 5 and I'm dividing by 5, so I'm just left with 2 minus 2 over this, and I'll multiply it out, but again, hold on, just watch for a second. So 3 times 4 over 25 minus 2/5 minus 2, but what do you notice happens up top? We get 2 minus 2. So this whole fraction equals 0. So it actually crosses at the ordered pair of 2/5 comma 0. And in the third case, we actually didn't get a horizontal asymptote, so it doesn't cross the horizontal asymptote because there isn't one, right? So let's go back and address that third case that we didn't talk about when it came to the horizontal asymptote, so that oblique or slant asymptote. And again, we only have to worry about this if we're actually talking about a top-heavy rational. Okay, the numerator's got a higher degree than the denominator. So when that happens, we have this very special skill that kicks in when we talk about the slant or oblique. Okay, so the slant or oblique asymptote is a slanted line, so not a flat horizontal line, or some other higher order polynomial that measures y values as x gets really, really small or x gets really, really big. So as that goes out to positive or negative infinity. So in the long run, what are the y values doing? Okay. So to find the oblique or slant asymptote, we're going to use polynomial long division or synthetic division when we can to identify a dividend and the remainder. So you think back to our last lesson, so one of the reasons why we looked at those skills is to apply it here in this particular lesson. So in identifying the slant asymptote, when we divide, the evenly divisible component is going to be our oblique. That's going to be what we want to find. Okay. So let's kind of look at some skills associated with that. So here we have a top-heavy rational, and again the question is, what is the oblique asymptote? Okay, so we're going to use synthetic division. So I want to set up an x squared, an x, and a constant. So the coefficient of x squared is 1, coefficient of x is 0, and the constant is 1. And I want to synthetically divide in, so it's x minus 4, I want the opposite of what I see, so I want 4. And then I'm going to drop and multiply. So 4 times 1 is 4, combine like terms I get 4, 4 times 4 is 16, and then I get 17. Okay. Now, that we do get a remainder, so let me kind of map out, let me write out what we just did. So x squared plus 1 over x minus 4 equals x plus 4 plus 17 over x minus 4. So we get a remainder here. That's our remainder piece. In the last section we were focused more on a remainder of 0, but in this case we get a remainder. But that piece, that's our oblique. So our oblique asymptote would be the equation y equals x plus 4. Okay, let's do another one. I'm going to divide. So so I'm going to make a list of all my coefficients. So 2, -1, and 10. And synthetically I'm going to divide in with a -3. Drop the 2, multiply, then combine like terms, multiply to get -6, and then combine like terms to get -7. Here we get positive 21 with a remainder of 31. So this becomes 2x minus 7 plus 31 over x plus 3. So the evenly divisible piece, not the remainder, that is our oblique asymptote. So it's y equals 2x minus 7. Okay. Well, what happens if we can't get away with synthetic? So we can't always use synthetic. So here's kind of a two illustration. Well, here one illustration we can, the other one we can't. But it is possible to have some other slant asymptote or oblique asymptote that isn't a line, that it's actually some other polynomial that we may or may not have seen from our transformations unit. So here I'm going to divide again. So make a list of my coefficients. So x cubed, x squared, x and constant. So 1, 0, 0, 1. And I'm going to synthetically divide in 2. Drop the 1. Multiply, combine, multiply, combine, multiply, and I get 9. Okay. So this, with its remainder, simplifies down to x squared plus 2x plus 4 plus 9 over x minus 2. But our oblique asymptote, in this case, is not a line, it's some parabola of some kind, is y equals x squared plus 2x plus 4. Now, not to make you panic, that's something that I would expect my pre-cal students to be good at. For us, I'm just exposing you to the idea that there does exist an oblique asymptote, and this is how one finds it. But I would not necessarily expect us to do something like this on an assessment. Okay, in this last case, dealing with the oblique asymptote, notice the denominator is x squared plus 3. That does not allow us to use synthetic. But luckily we do have polynomial long division, so sometimes we're just stuck to having to use that. Okay, so if you remember, I start by asking myself what do I multiply x squared by to get it to say 2x to the 4th, and that would be 2x squared. And then I want to distribute that. So that's 2x squared times x squared is 2x to the 4th plus 3x squared. And I'll subtract there. And when I subtract, of course, the x to the 4th cancel out. And I actually get, you gotta be careful with this because the 3x and 3x squared are not like terms. So those aren't going to cancel out, or I'm not going to get a 6 anywhere at all out of that. But I do end up with negative 3x squared minus 3x. And you're probably thinking, where'd the negative come from? Remember, we subtracted that bottom statement. So even though it says plus 3x squared, it's really the top minus the bottom. So when I minus the bottom, I get a negative 3x squared. Okay, now what? Well, what do I multiply x squared by to get it to say negative 3x squared? And that's just minus 3. So distribute that in, and we get negative 3x squared minus 9. So then we subtract. And of course, the 3x squareds cancel out. And you're going to be very careful about your signs on this one. The 3x and the 9, those don't combine. So I still have a negative 3x, but what about the 9? Is that going to be positive or negative? Remember, we're subtracting a negative, so that means it's really plus 9. Now, what does that have to do with anything? I don't have, I'm kind of done. That's sort of my remainder at this point. So when I divide, I get 2x squared minus 3 plus, and that's where that remainder of negative 3x plus 9 over x squared plus 3 comes in. So what actually is my oblique asymptote? My oblique is that evenly divisible piece again. So 2x squared minus 3. So again, if you see a top-heavy rational, that's where this division piece kicks in. And all of this does is tell us the equation of the oblique asymptote. And so it's out there. It does happen.